Today we're going to do 277A, and it's 1 through 25 odd. And this deals with division of polynomials. Now we're going to show you the harder method first, and then tomorrow we're going to go to the easy method. The trouble with the easy method is it doesn't always work. It's way faster, but it only works in certain cases. So in a more complicated case, you have to use the harder version. So take a look. I'll do number 2. Number 2 says, take the quadratic x squared plus 4x minus 3 and divide it by the binomial x minus 1. So the longer way to do it is called long division. And we do long division by setting up a multiplication box. And this is going to be entered inside the box. And that is going to be put on the left side of the box. So I don't know how big the box is, but I know that the left side has 2 squares. It's too deep. So I'm going to put x and negative 1, and then I'll cut off one of the columns, and x squared goes in this first box right there. Well, if that is x squared, what goes above it? Why? We're asking what times x equals x squared, and the answer is x. Okay? Well, I now have x on the top and negative 1 on the bottom left, so what is the bottom left box? Negative x. And then if you remember how these multiplications work, the diagonals all have the same degree, and so this square here and this square here will both be x's, and they're going to add up to be negative 4x, or positive 4x. So what goes in this missing square? Right, what plus negative x equals 4x? And the answer is 5x. So what times x equals 5x? 5, and 5 times negative 1 is negative 5. And then we'll add one more. What would go in this box to add to negative 5 to equal negative 3? 2. So I put plus 2 there. Well, how many times does x go into 2? None. So that 2 ends up being the remainder. And there are 2 ways to deal with the remainder. One is to say x plus 5 remainder 2. The other way is to say, well, it's actually 2 cut into x minus 1 pieces, which is x plus 5 plus 2 over x minus 1. Now that might seem totally crazy to you, but if I show you this, it will make sense. How many times does 4 go into 21? So 21 divided by 4. 5 remainder 1, which is also 5 plus 1 over the original divisor, 4. 5 and a fourth. So a remainder is just a piece of the 4. We were hoping for 4 of those, but we didn't have 4. All we had was 1 left over, so it didn't go in evenly. So it's just 5 plus 1/4. How do they do this in the back of the book? Okay, and they probably set it up as 2 different functions. Yeah, that's silly. But anyway, so just state the remainder. But know that really 5 plus 1/4 is true. So if I look at this, maybe if it'll lighten up. So x squared plus 4x minus 3 over x minus 1 is equivalent to x plus 5 remainder 2. But that doesn't make any sense as an equation, right? So if I were to graph it, I would say x plus 5 plus 2 over x minus 1. And actually, these two equations are absolutely identical. This one is the improper fraction version, like 21/4, and this is the mixed numbered version, sort of like 5 1/4. That's all we're doing there. Now, what if there is no remainder? Well, it's nice, but what if there's no remainder? What do we know about the original problem? So if you look at this, if I divide those and I get remainder 0, what does that tell me about x squared plus 4x minus 3? It means that x minus 1 was a factor, right? 20 divided by 4. 4 goes into 20 evenly, which means that 4 is a factor of 20. So if it works, essentially, we had x minus 1 times something over x minus 1, and those cancel. But if it doesn't go into it, if the remainder is not 0, then we can guarantee that x minus 1 is not a factor of the numerator. Okay? Now, if it does go in, so in this case, x equals 1 is a whole or an asymptote. Do you remember? If it divides out, then it is a whole. But if it doesn't divide out, then x equals 1 is an asymptote. So in this case, because x minus 1 did not go in evenly, x equals 1 is an asymptote. If it does go in evenly, it means it was a factor, so the associated root would be a whole on the original graph. Okay, that's a lot to process. Let's try another one. Let's look at number 4. So I look at the denominator, x plus 5, so I put that on the left. And I don't know how long this is going to be, but I know that the first term is 3x squared. So what times x equals 3x squared? 3x, and now 3x times 5 is 15x. And then these two boxes have to add to be negative 13. Is that a negative? Yeah. So 15 plus what is negative 13? So I need to take away 15 to get to 0, an additional 13, so minus 28. X. And then what times x is negative 28x? Negative 28. And then negative 28 times 5 is going to be 140. Minus 140. Did that go in evenly? Not even close. What's the remainder? I need to add another 130, so it would be 3x minus 28, remainder 130. Or plus 130 over x plus 5. Okay, now there's something you have to be careful about. If you look at number 10, so on the left side, I have 2x plus 3. Do you see a potential problem with number 10? Look at the numerator. We're missing degrees. We're missing the x squared and the x. So we still have to account for them, and it might turn out that it doesn't really matter, but it also might turn out that it does matter. So I'm going to put in 8x to the third. 2x times what is 8x to the third? 4x squared. And then 4x squared times 3 is 12x squared. And now these two boxes need to add up to be 0, because there is no x squared term. So this needs to be negative 12x squared. And then 2x times what is negative 12x squared? Negative 6x. And negative 6x times 3 is negative 18x. And negative 18x and what add up to be 0. So this will be 18x 2x goes into 18x 9 times, and 9 times 3 is 27. Does this have a remainder? No. So that is the answer, which means 2x plus 3 is a factor of the original problem, and x equals negative 3 halves is a whole because it divided out. Okay? I want to do one more. Number 18. Number 18 looks quite nasty. So, I'm going to need some room here. Okay. So, there's a different sort of problem here. We already know how to deal with missing numbers in the numerator. We just have to add up to be 0, but look at the denominator. What are we missing in the denominator? X to the third and x squared. How do we deal with that? We put in blank spaces, essentially. So on the left side, I have 3x to the fourth, and then 0x to the third, and then 0x squared, minus 2x, and then plus 1. Now, it might turn out that we don't need those, but there's no way to tell at the beginning. And there is a good thing about having a 0 in one of the rows. The whole row is going to be 0, right? Because the stuff on the left side times the stuff on the top creates every square, and if one of those is 0, then the whole square is going to be 0. And again, I don't know how long this is going to be, so I'll just draw those out. So, negative 9x to the 6th. How many times does 3x to the 4th go into negative 9x to the 6th? Negative 3x squared. And then negative 3x squared times 0x to the 3rd is 0x to the 5th. And then I know this will be 0x to the 4th, 0x to the 3rd, 0x squared, 0x, and 0. Okay, now the same thing is true of the next row. 0, 0, 0, 0, 0, 0. Well, if they're all zeros, why do I even bother writing them? I mean, why don't I just delete these two rows? The diagonals will no longer match. And you can do it that way if you're careful, but it's quite hard to figure out. So I need these as placeholders. So all of my x to the fourths will be in a row. If you delete those two rows, then the diagonals won't match anymore. Okay, so negative 3x squared and negative 2x make 6x to the third and negative 3x squared. Okay, so now I look at this diagonal. That is my x to the fifth diagonal. How many x to the fifths are there in the numerator? None, so that's nice. So this will be 0x to the fifth. And if that's 0, what do I know about that whole column? That whole column has to be 0, because 3 times 0 is 0. And now, if that's 0, then the whole thing ends up being 0. Okay? And then I look at this diagonal. How many x to the fourths are in the numerator? 7, so how many do I need to add on that top box? 0 plus 0 plus 7. So I'll put a 7 there. Uh-oh. Did I mess up? Hopefully I made a mistake. Do you see a mistake somewhere? Okay, well, how many times does 3 go into 7? 1 1/3 or 7/3. I would stick with fractions. So this will be plus 7/3. Okay. Did I make a mistake somewhere? I don't think so. So 7/3. No, just 7/3 x, right? Or just 7/3. Okay. So 7/3 times 0 is 0. 7/3 times 0 is 0. 7/3 times -2 is going to be -14/3. And then 7/3 times 1 is 7/3. So I look here. 6x to the third plus 0 plus 0 plus what is 7x to the fourth? Or sorry, x to the third. So I need to add up to be this. So I need -8x to the third. Okay. And then how many times does 3x to the fourth go into -8x to the third? It doesn't. So what is this? It's a piece of the remainder. How many pieces will this remainder have? 4 of them. It'll have an x to the third, an x squared, an x, and a constant. So that is one piece of the remainder. So I go to the next diagonal. -3x squared plus 0 plus 0 plus 0 plus what equals 0. So this is 3x squared. So that's another piece of the remainder. And then all of those need to add up to be, oh, this is an x, right? They all need to add up to be 0x, so plus 14/3 x. And then all of the constants need to add up to be 5. So what is 5 minus 7/3? 8/3. Do you have to times the -8? Oh, so do I need to fill this out? No, because there is no number up here. All of this is just going to be lumped together as a remainder. There is, and if you put a number there, it's essentially turning it into a decimal. And if you do that, it will keep going on forever. So instead of dealing with decimals, we're just going to go straight to remainders. So that's a good question. So the answer is -3x squared plus 7/3. Remainder, -8x to the third plus 3x squared plus 14/3 x plus 8/3. Okay. Now, your remainder will always be 1 degree less than your original denominator, right? This was an x to the fourth, so my remainder can be as big as x to the third. Just like when I did 21 divide 4, I got 5 1/4. But what if I did 22 divide 4? 5 2/4. 23 over 4 would be 5 3/4. And then 24 over 4 would be 5 4/4. But that's really just 6. So your remainder will always have one smaller value, at least one smaller value than the original divisor. Because if they're the same size, then it actually would have gone into it. Okay? All right, 1 through 25 odd. Good luck.